Hi and welcome to day 10 of the advent of compiler optimizations. Today we're going to look at loops and specifically some of the unrolling tricks that compilers can pull. Let's have a look in Compiler Explorer. So over here we're going to be using ARM v7 just for old time's sake for me. And I am going to write a simple loop, just like we did a couple of days back. Let's do another sum, and I'm going to take a stood span this time. So a stood span is similar to a vector in as much as it has a pointer and a size, but it's non-owning. It refers to another area of memory, so it's a way of accepting pointers to existing C-like arrays or stood vectors or anything that looks like a contiguous range of memory. So let's take a span called span, and then we're going to do int total, and we're going to do that, and we're going to say for auto, because we know we can do this now, let's do val in the span, total plus equals val, return total. So we're not giving the compiler any hints here other than, oh, wait a second, I'm missing my stood equals C++ to C, and wall Wextra, I don't know how I lost those, W conversion. Now we're in a good spot. Okay, fabulous. So here we can see the code that's been generated, and it's pretty straightforward. The compiler doesn't know how big the span is. Spans have two variations. They can either be dynamically sized, in which case you'll see here that it's passed int, and the second template parameter is this magic value here, which is effectively -1. And that says that the span is dynamically sized. So now the compiler has to check. So the first thing it does is it checks R1 with 0. Now in ARM v7, the first parameters are passed in R0 and R1 and R2 and so on. And because a span is just a pointer and a size, the compiler can pack them into two registers. And so the ABI allows us to pass an 8-byte, this is a 32-bit machine, an 8-byte span struct in two adjacent registers. That means that the pointer is in R0 and the size is in R1. So we're comparing R1 here with 0, and then if it's equal to 0, that means that there's no elements, and so we're just going straight to the end, returning 0. Otherwise, we are shifting left the size by 2, so we're multiplying by 4, which effectively gives us the byte size of the array that we're going to be iterating over. We are copying the input parameter, the pointer to it, into R2, and we're setting R0, which is going to be our running total, to be 0. And then our loop is pretty straightforward. We read the next integer and we put it into R3, and then this syntax, the comma #4 at the end, also auto increments R2. So it reads from R2 and then it moves R2 4 bytes forward. We subtract 4 from our size, we add to our running total, and then we branch, if the size wasn't equal to 0, back to L2. Now, it's a bit unusual why the compiler has decided to multiply by 4 and then subtract each iteration by 4 when it could just avoid that and just decrement. Who knows why it did that, but it's a pretty straightforward loop, and this VXLR is effectively a return instruction. So far, so great. Now, the cool things about spans is that we can actually pass, as part of the type, a compile time size for that span. Let's have a look at what happens when we do that. So I'm going to put 8 here, which means that this is now a compile time known set of 8 integers, and you can already see what's happening on the right hand side. The compiler is pushing a bunch of registers onto the stack, it's reading the first value, then it's reading the next two values. So this IB instruction is, the LDM is a load multiple, IB is increment before, so it's going to increment R0 before it does the first read, and then again after that first read. So it's moving R0 forward to get R2 and R3, and from now onwards it's reading one and adding, reading and adding, reading and adding, reading and adding, reading and adding, and then it sort of accounts for the last few adds that need to be completed, and it gets the result in R0. So it has kept the execution units busy doing reads and adds, and there's no looping overhead whatsoever. The whole thing has been unrolled, and this is great. We've saved two instructions, the add and the compare, and the branch, in fact, for each iteration. So 3 instructions for each iteration, and presumably within certain ARM CPUs, some of these loads and adds could run concurrently. So fantastic. If we experiment with other values here, we can see what the compiler does for different sizes of blocks. So in this particular instance, you can see it kind of does a bigger load multiple at the beginning. Let's make this even huger. Let's make it 64. What does it do now? Interestingly, it falls back to just doing one at a time for 64 of them, which is, I would imagine it might chunk up into like batches of 16 and do 16 at a time, but it doesn't. So let's see if we can find where the boundary is. 40, and we're still doing this sort of clever special case stuff. 50, and we've broken down. So somewhere between those two. 46 is clever. 48 is still quite clever. 49 is clever. So it looks like 50. So there is some heuristic somewhere in the compiler set to around 50. It's probably tunable with a parameter, honestly, where it stops unrolling small loops of this size and then finding all the opportunities within it. That's interesting, right? So the compiler will sometimes unroll loops if it knows the trip count, and that can unlock other optimization opportunities. Tomorrow we're going to look at something completely different, so I'll look forward to seeing you then.